So we are today starting section 6.1, which is where we're going to talk about, or chapter 6 is where we talk about gathering and describing data. Lots of times, like if I teach the level below this, we do this topic first, and then do probability. But in this book, we've done probability first, and now we're going to talk about gathering and describing data. Okay. So in our first two chapters, chapters 2 to 5, we looked at the probability distributions of a random variable. So like one such random variable could be 1/9 x squared, where x is between 0 and 3. Okay. And so in those situations, we actually knew the distribution of the random variable. But in practice, you're usually not going to know the actual distribution. And so what you want to do is you want to figure out everything you can about this actual distribution using data that you gather through an experiment. So our population, we're going to define our population as all the possible observations available from a particular probability distribution. So we assume that there is some underlying probability distribution that governs everything. Okay? So if we want to talk about like the heights of everyone on campus, we're going to assume that there is some kind of distribution that would describe the heights of everyone on campus. We just don't know what it is. But that would be our population, would be everyone on campus that we want everyone on campus, and we want to look at the heights of everyone. The parameter is a property of an underlying probability distribution. So remember some of our distributions, like for the binomial distribution, the parameters are n and p, or for a normal distribution, the parameters, the things that control the shape of the distribution, are the mean and standard deviation. So for example, an investigator wants to know what proportion of voters in the U.S. will vote Republican in the next election. In this situation, our population would be the voters in the U.S., and the parameter is the proportion of people in the U.S. who will vote Republican. And now again, for this parameter, this is what my value would be if I knew all the data in the population. So if I actually knew what everyone in the U.S. was, then the parameter would be that proportion who vote Republican. So for our next example, a toothpaste company would like to know what proportion of dentists recommend the brand it produces. Identify a population and a parameter. Okay. Now, so for population, like, it's your people of interest. Okay. So what would the population be? What are some possible populations that we could have? Okay. All dentists. Okay, now it's not very specific, so I don't know. This could be all dentists in the U.S., or they could have said all dentists in Utah, or they could have said all dentists in the world. They didn't say, so we'll just go with all dentists. Okay. But sometimes we do have our population narrowed down a bit. It's just whatever we are interested in. And the parameter would be proportion that recommend the toothpaste. Now, in practice, it's usually not feasible to collect data from every individual in a given population. Why not? What do you think would stop me from collecting the data on every individual?
There's too many of them.
There are too many.
It would cost too much.
Cost too much, too expensive.
Availability subjects.
Ooh, the availability of subjects. We know that for, say, the census, it's very difficult to actually find everyone at home and get them to all actually respond to your survey. Okay, so too many, too expensive, too much time. Etc. So it's usually very impractical to try and actually collect data on everything in the population. However, if you could get data from the entire population, then you could actually figure out the true underlying probability mass function or probability density function. Okay, so if we had all of the data, then we can know the actual true underlying function. And we would know the actual parameters. So our sample, what we're going to do instead of taking data on the entire population is we take a sample, which would be a subset of the population on which we collect data. And our statistic is a random variable whose value we compute from the data in the sample. And the statistic is used to estimate our unknown parameter. And once we estimate our unknown parameter, then we can draw conclusions about our overall population. And this is what we call inferential statistics. Okay. The whole point of statistics is we want to try and deduce properties about the population using the information in our sample. Okay. So that's inferential statistics. You'll also hear us describe descriptive statistics, which is all we do is just summarize our data graphically, numerically, write up a report on it. So if all you're doing is describing the data, it's just descriptive statistics. That's usually what we make you do in like high school classes or even junior high classes. But once you start looking at the data in your sample and trying to draw conclusions about your population, now it becomes inferential statistics.
So do you usually use descriptive statistics in inferential statistics?
Yep. So before we can do any inferential statistics, we will need the descriptive statistics to start with. So this is an example. So this blue line is the underlying probability distribution. So I've drawn the blue line. This is what it would look like if I had all the data in the population. Now the black bars are for the data in one sample. So I just generated a sample. Notice it doesn't line up exactly with my curve. No, but it is fairly close. Okay? And so what happens is when you draw a sample, you're not going to get the exact curve yet because you don't have all the data in the distribution. But you might get a general idea of what the shape of the original distribution is. So when you want to choose a sample, what we want is we want a representative sample. So we want to make sure that our sample actually is going to give us accurate information about the population. Otherwise, our study's not going to do us any good. So when we say our sample gives us good information about the population, what we want is we want to make sure that our sample is representative of our population. We want to make sure it shares the same characteristics, it has the same distribution. We want to make sure it will tell us good information about our population. Because if your sample is poorly chosen, your statistic is going to give you bad estimates of your population parameters. So for example, suppose the population for the breakup survey in all adults in the U.S. is all adults in the U.S., and then the parameter of interest is the percentage of U.S. adults who are shocked by Carmen Electra's and Dave Navarro's breakup. I don't even know who that is. Okay. So first of all, is the sample used in the survey representative of the population? Okay. So I copied this from something, and it didn't tell us what the sample was. Okay. I think the sample is people who responded to, is Us a magazine or like online site or something? Let's make it up and say this was a U.S. Weekly survey. Okay. So to start with, is the sample in the survey representative of the population? Okay. So our sample is people who responded to a U.S. Weekly survey. Okay. What was our population? All adults in the U.S. Okay. So do you think that your sample of people who responded to Us Weekly is representative of all adults in the United States?
No.
Okay. Why not?
You never use just the inferential survey that is all the people in the U.S.
Okay.
It's a targeted population as well. It's not necessarily a whole bunch of different types of people that don't even look at that magazine.
Mm-hmm. So you're saying that Us Weekly is a targeted audience, and that there's a lot of people like me, obviously, that don't even look at that magazine or know who these people are. Okay, so you have a whole bunch of people in the U.S. that aren't going to be represented by the people who responded to the survey. And so if the people that responded to this Us Weekly survey aren't representative of the whole U.S. population, then is our statistic going to be a good estimate of our parameter? Is the proportion of people who said yes in the survey going to represent the proportion of all people in the U.S. who were shocked? No. And this next scenario is very much the same thing. So, like, Ann Landers asked people this question. So she said, if you had to do it again, would you still have children? And she received over 10,000 responses, which that's a very good sample size. Okay, usually if you get 10,000 of anything, that would be a very good sign that your sample is probably representative. However, okay, so she asked people, she received over 10,000 responses, 70% of the respondents answered no. Okay. Now, let's say the population is all North American parents, and the parameter is percentage who would not have kids if they could do it over again. Okay. So do you think her sample adequately represented the population? Okay. Now, it doesn't say specifically how she asked this. Like, we don't know, maybe it did reach all Americans. But did every American necessarily bother responding?
It says it's to her readers on that.
Oh, to her readers. Okay. So it only went to her readers. Do you think that maybe her readers could be a targeted audience? So maybe, like, I don't know her either. I'm not very good at my pop culture. But maybe the people who read her already are kind of a little biased against not having children. So maybe, again, we could have a targeted audience. And there's something else here. Okay, so what happened is she asked the question, and then people sent in their responses. This is what we call self-response, or okay. Anytime people choose whether or not to respond to something, they usually already have strong opinions. If you're going to bother to send in a response, especially when you had to put in an envelope and put a stamp on it, you probably feel very strongly about this question. Okay, so anything where people self-choose to respond to a survey, you're going to get biased results. Have you ever noticed if you look at reviews on things online, lots of times you either have very strong opinions for it and you have very strong opinions against it, okay? Because otherwise you don't care enough to take the time to make the review. So we found that self-selected surveys, so people who choose if they want to respond, don't give us very accurate results because they have stronger opinions than the overall population. So for our next question is, how would you select a representative sample to carry out their survey? So what is something that you could do to get rid of that self-selection and maybe that targeted audience?
Go out and talk to people.
Okay, go out and talk to people. So to be more specific, we would want to talk to everyone, right? And not just her readers, but we'd want to talk to all types of parents. Okay, any other thoughts?
Like the answer to the question, just yes or no.
Say.
Like, instead of like, you know how they did like, well, I don't know, when you say self-selected responses, it sounds like they don't have, like, they could write whatever they wanted, really.
Oh.
So if you just made it like a yes or no question.
I think it still could have been a yes or no. I don't know. Self-selected is more the people that decided it was worth their time to send in an envelope, send in a response. So things you could do is, instead of letting them choose whether or not they respond, you could approach them and ask them. So you could ask people, and the other thing we said is that we need to ask people from the general population. Now, does that mean that you can't include any of Anne's readers? Okay. Well, they're still part of the population, so you could probably still include some of her readers, but you need to make sure that you include all types of people. One of the ways that we ensure that a sample is representative of the population is we choose a random sample. For a random sample, that means we choose the people in the population randomly. So instead of us picking people or even just going like door to door to door until we get tired of it, like that wouldn't be very random either. We look at our entire population and just randomly choose the people that we're going to survey. And when we randomly choose it, that means we use some kind of probability-based mechanics. The only one we're really going to talk about in this class is for a simple random sample, so the last bullet point. For a simple random sample, you just make every object equally likely to be chosen. Now, when you use this random process, then our sample is going to be more representative of our population. Okay? Also, part of it being randomly selected is that humans have no choice in it. Okay? So you as a surveyor do not get to choose who you talk to. It should be very random with no input from you. One of the ways that you can make this random is you can assign numbers to all the objects in the population and then just use a random number generator to choose your data. So, and for this next example 5, so here are some bad examples of random selection, and let's try and figure out why it would be bad. So for number 1, 4 students want to determine which Logan grocery store has the lowest prices. Each student makes a list of the items he buys most often, and students compare prices on those items at the local stores. Okay, what can you see would be wrong with this scenario? What would make our data inaccurate?
They're not shopping for the same items necessarily.
Okay. They could be shopping for different items. Could also go the other way, and maybe they only shop for the same items. These are college students. Maybe they're all only shopping for ramen noodles or something like that. Okay, so it could swing either way. Like they could shop for completely different things. They could all shop for the same thing. Maybe the things that they usually shop for are the things that are always on sale at a specific store. Okay. Or maybe they only buy things that are on sale when they come on sale. So maybe they're just grabbing the sales at Lee's, whereas Walmart might have it cheaper usually, but they only bought the things that were on sale. So you can think of a lot of things like this that could throw in some bias. So for our next example, like a teacher wishes to know what proportion of the students that take Stats 3000 are female. She teaches one section of Stats 3000 in the spring, so she chooses this section for her sample. Can you think of any issues with this?
Well, she's only sampling like one section of it.
Okay.
Not just the whole thing.
So only sampling one section. And what could happen if she only samples one section? Perhaps that spring there just happens to be a lot of females that just happen to sign up for that class. So maybe it's usually like 40%, but maybe that spring it happens to be 80%, just out of a weird coincidence. So is that going to be representative of all students that take Stats 3000? No. So we could say things like, by coincidence, we could have more or less females than usual. I guess I should write something on number 1. Something like, they could choose all cheap items, or all the same items, etc. So, any questions to this point?
To make the first one more like representative, could you exclude like the sale items, or like could you just be like you have to like look at stuff that's only normal.
Okay, so you could decide it either way. So part of your question might just be what are the normal prices in the stores, and then you would want to exclude sales items. But if you're a person that really likes to do sales items, well, you might want to include that in the study because you might want to see if that makes it cheaper. So what you could really do to make it fair is ahead of time think of a lot of things you could buy at the grocery store. So make a list of like 200 or 300 items and just randomly pick like 30 items or so, and then go compare those items at each store and compare the same things at each store. And that would help eliminate a lot of your bias. Okay. So our textbook defines population as the set of all possible observations from an underlying probability distribution. That's usually not the way it's approached in a statistics textbook. So I'm going to just rephrase it, and this is the way that we usually approach it in a statistics textbook. Okay. So usually our population is just the set of all of our people or items, events, objects, etc. that are of interest. So for example, possible populations could be everyone in the US, or every Honda car built in 2013, or every English major at 4 universities in Utah. Okay. Notice on these that you can make your population as specific or as general as you want. Okay. So you can have a population be everyone in the US, but someone else might want to do a study and they might want to do everyone in the world, or everyone in North America, or everyone in Utah. So your population is just what you specifically are interested in. And your sample is, again, the smaller part of your population on which we actually collect data. So instead of sampling everyone in the US, you could do every 1,000th person. Or instead of every Honda car in 2013, you could do every 500th car to come out of the factory. Or instead of every English major, you could just sample 300 English majors. Actually, that might be all the English majors in Utah. I don't know how popular that is. So once you take your sample, then you have what we call the data set, which is your actual observations. We'll use the notation x1, x2, up to xn. Those are just your actual values. You can have categorical data, also called the nominal, and the observations fall into one of several categories. This would be things like your eye color, because your eye color can be green, blue, brown, hazel, etc. And so you only fall into categories, there's no numbers with it. Binary data is the special case of categorical when you only have one of two categories. And numerical data, which we also call quantitative, the data is either like integers or real numbers. Okay? And even more than that, it needs to be something where arithmetic makes sense to do with this data. So if you add the numbers together or you take the average of the numbers, does that give you something reasonable? And if you have this numerical data, you can analyze it as a continuous random variable. Whereas your categorical, what kind of random variable would that fall under? It'd be more of a discrete random variable. So for example 6, I want to know the final grades percentage of all the students in the US in introductory statistics courses. So to start with, what is the population here?
All students in the U.S.
So all students in US in intro stats. What could be a possible sample? There's not a specific right answer to this, but what could be a possible sample?
So maybe the average of the
Okay. Well, do we want to go out and look at every student in the U.S.? Would that be kind of difficult to actually find the data for every student in the U.S.? What if we pick like 300, 500, or 1,000 students in the U.S. to look at first? And you said we want to make sure they're representative, so we should probably choose them randomly. So we could choose like 1,000 randomly chosen students. Okay. Now, I don't want just any 1,000 students. I do want to make sure that they are still in the U.S. intro stats. So the sample is the actual students. Now my variable, though, I'm interested in the final grades. So my variable itself, the thing I actually measure, is the final grades of the students. And it does say that it is the percentage, so is this variable numerical or categorical?
Numerical.
Numerical. So for our next example, I just want to go through and look at each thing and see if it's categorical or quantitative. Remember, quantitative is the same thing as numerical. So the first one is the amount of carbon dioxide produced by a car. Okay, I say numerical because you'd probably be measuring it in, well, however you measure carbon dioxide. Parts per million. Okay, so we probably measure in parts per million, and you'd probably get a numerical answer. Now, could it be possible to change this into a categorical answer? How could you measure it to some way get a categorical? Okay, but only measure the amount of carbon dioxide.
Could you like put like the different, like you have the ranges in categories, like 100 to like 200?
Yep. So if you break it up into ranges or categories, then you could potentially make it into categorical. So you could do like 0 to 100, 100 to 150, or you could even just call it low, medium, high, or something. So it's always possible to take a numerical value and break it up into categories. But when in doubt, if it sounds like it's something that could be quantitative or numerical, that's probably what we're going to go with. That's usually a little bit easier for us to analyze. So number 2, though, color of a car, that would have to be categorical. Breed of a horse would be categorical. Length of time to graduate from college, quantitative, because you could put numbers to it. Your social security number.
Categorical.
Okay, so it's actually not quantitative. What makes it? What stops it from being quantitative?
It's a specific number to each person.
Okay.
You can't just like add them all up and get a result.
So, like, if I added our 2 social security numbers, that's not going to tell me anything meaningful, right? Or if I take the average, that doesn't tell me anything meaningful. Also, when you think about it for your social security number, is it a number or is it just a symbol? Like, would it have meant the same thing instead of if using numerical digits, they'd use like Greek alphabet letters or just random symbols? Could they have still made social security random symbols? Okay, so really when you think about this, this is really just a type of identification. Okay, and if you had to choose one, we would call it categorical. Because even though it's technically a number, it's not really anything numerical, it's just those were the random symbols that they happen to choose. The length of your favorite song would be quantitative, and the artist of your favorite song would be categorical. So that is our first section. Any questions? So we first learned a little bit about gathering data. The next thing we need to learn is how to actually present our data. So presenting our data helps us actually understand our information. Data can either be our categorical, sometimes called nominal or qualitative, if you see those terms in the future, in which data corresponds to your categories or types, or it can be numerical, quantitative, which consists of our numbers. And we have both graphical and numeric methods of summarizing the data. In this section we're going to do graphical, and the next section we'll do numerical. And if you use poorly constructed graphics for your data presentation, then you can obscure the information or appear to exaggerate relationships. Okay? Have you heard of the book How to Lie with Statistics? Okay. It's a fairly famous book. But what happens is you can change a graph so that it looks like it's saying it's something it's not. And we really need to be careful when we do statistics that we give results that are accurate and not misleading. So to start with, we have categorical data. So if you have categorical data, you can use pie charts or bar charts. I'm sure most of you have used these at some point in your life, or at least seen them. So a pie chart is we look at our data set, we find each category, and we figure out the percentage that goes in that category, and then we put it on the pie chart with the representative sizes. Okay. So like for example A, here's the market shares for the major GPS brands, and tell me each company and the percentage. So you can see my pie chart tells me each category and the percentage, and the size of each pie piece is proportional to its percentage. The bar chart presents the frequencies of our categorical data visually. So each category has the corresponding bar whose height is proportional to the frequency or percentage associated with that category. Bar charts are useful for comparing our categories, and well, so are pie charts. And you can use either frequencies or your counts or percentages when you make a bar chart. So when you look at this, this is my bar chart. So I can see that Garmin has about 47%, TomTom has about 19%, Magellan 17%, etc. Okay, notice in the bar chart that my bars aren't necessarily in order. If you ever put the bars in order of their height, then it becomes what is called a Pareto chart, and it's just a specific type, and you put it in order of frequency. We like the Pareto charts just because it makes it nicer to our eyes. Our eyes just look like it a little bit better, and it makes it easy to look at it and immediately see what is the biggest category, what is the smallest category. So here is just one example of a way that you could use a graphic in a misleading manner. So when you look at this first chart, okay, so we just have A, B, and C. We don't know what they are. But notice when you look at this first chart, doesn't C look like it's about twice as big as A? And so if we had, let's say these were 3 different types of toothpaste, and if I looked at it, I would think that toothpaste brand C is a lot more popular than brand A. But what happened is, notice when you look at their axis, it starts at 80. So they truncated their axis, whereas if you actually look at it and you start all the way at 0 and go up, notice A is almost as high as C. There's actually not that big of a difference between the 3 brands. So just something to look for when you look at charts that people produce in the future. So that was for our categorical data. You have 2 options, bar chart or pie chart. For our next example, we have numerical data. And numerical data is we represent with histograms. So they look like bar charts, but it's for numerical data. What we do for a histogram is, because our data isn't already in categories, we need to artificially create categories, which we call our bins or classes, depending on which software you want to use. And when you create these bins, you make, or your classes, you make the area of each rectangle proportional to the number of observations in that category. So if all of your bins have equal width, then instead of worrying about the height of the bar or the area of the bar, you can just look at the height of each bar and make it proportional. I'll come back to that bullet point. And we need to make, actually I'll come back to that one too. Let's just start our histogram, and then once we draw it, then we can talk about the other 2 things. So here are IQ scores for 60 randomly chosen 5th graders. Construct a histogram. So my IQ scores, 60 scores. And it's easier if we reorder it first, so here are my reordered scores. The first step to make a histogram is you need to choose your classes, or your bins. And then once you have that, you need to count, or your frequency, how many observations are in each bin. So it looks like our data runs from 81 to 145. How wide of a bin do you want to use? There's not necessarily a right answer here. Do you want to count by 7s, 10s, 15s, 20s? Okay, I was going to say 15. Let's go 15. So because I want to count by 15s, it's easier for me if instead of starting at 81, I'm going to start with 80, just because that's easier for me. So I'm going to go from 80 to 95. Now one of the things you need to do here is you need to figure out which endpoint you're going to include in each class. Okay, so if I want to include like the 80, then my next class starts at 95 again, and I don't want to include, so my next class would go from 95 to 110, and I don't want to include 95 in both bins. That would get confusing if I have a 95. So we need to figure out which one we want to include it in. Okay, there's not a right or wrong answer for this either. So just decide, do you want to include the lower number or the higher number for each class? Okay, let's include the lower number. So my first class or bin will go from 80, include the 80, to 95, don't include the 95. So my next class would be from 95 included to 110, not included. Then 110 to 125, and 125 to 140. And it looks like I need to keep going. So 140 to 155. So we created our classes. Again, there was not a right answer. We just picked the width that we wanted, and we started writing down our categories or our bins. Now I need to go through and count how many observations fall in each one of these bins. So from 80 to 95, not including the 95. We have 1, 2, 3, 4, 5. Now I need to count from 95 to 110. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. Oh, don't include the 110. So I'm at 16. Right? You guys can correct me if I'm wrong. Okay, so go ahead and count the next classes. So what is the next one? Did anyone already count it?
23.
23. Next one? I got 14. Anyone else? And 140 to 155, it looks like just 2 of them. We should probably make sure those add up back up to 60. Okay, they add up to 60. Once I have that, then I come over to my graph and I just need to start labeling. So we have 80. I think I can go 2 spaces. 95, 110, 125, 140, 155. And I need to label my axis. I'm going to go with a scale of 3. So from 80 to 95, I have 5 people. So I draw my bar up to 5. Oh, sorry. It's from 80 to 95, goes up to 5. Then 95 to 110 goes all the way up to 16. Okay. 110 to 125 goes to 23. 125 to 140 has 14. And 140 to 155 has 2. And that is my histogram. Notice I did choose equal width bins, and because I did equal width bins, I could just draw the height of each rectangle, just went to the count, and that made it very easy. Okay, instead of doing counts, I could have changed these to percentages if I wanted to, and did the percentages. Either way is viable. Notice the shape of this. Can you imagine if I took enough classes and I had enough data, that this would eventually, think of calculus, get smoothed out into a smooth curve, and it would become a probability density function. That's why the comment above says you can think of a probability density function as just a smoothed out histogram. Now, when you choose your bin width, so I did tell you there's not a right or wrong answer because it's difficult to just tell it easily, okay, without doing mental calculations. But you will notice as you go through and do problems, if you pick bins that are too small, then you get graphs that look very spiky, okay, and kind of annoying to look at. If you pick bins that are too big, then you lose a lot of the information in your distribution. So let's look at an example of what a histogram looks like with different bin widths. So these are the same IQ scores, for example 10, same IQ score, same data set, and all I've done for these histograms is chosen different bin widths. Okay, so for a bin width of 2, okay, bin width of 7, and bin width of 20. Okay. Notice the difference in the way these look. Okay, even the difference in the way our histogram looked compared to this, because we chose a bin width of 15. So looking at this, which one do you like the most for being able to see the most information? Okay. 7 seems the most pleasing to us. It's not too spiky, but it still gives us more information than 20. Okay. Now this is difficult to know in advance how many bins you should do. If you were trying to do a presentation or really give a report, I'd probably try around with several different bin widths until I found one that looked good. Okay. Lots of times computers will try and automatically select it for you. They don't always pick the best thing, but usually their automatic selections are fairly good. Although I've noticed a lot of the softwares, if possible, will just count by 5s or 10s because it does seem more natural to us when we view it. So any questions to this point? Questions on histograms? Okay. Now that I have shown it to you once, I'm going to tell you that when you do your homework, you are welcome to use any software to compute any of this. You do not have to do it by hand. If you have access to the software. Okay. So this is a good point, I think, to talk about that. So if you go to your Canvas page, I put it in 2 places. So if you go to this homework, okay, you'll notice that I put up here something called Megastat. Okay. You are welcome to use any software. There are quite a few different free ones out there that you could use. You could even go pay a lot if you wanted something else. Okay. But this is a free plugin to Excel. It's really easy to use, very much of a point and click. So it's called Megastat. It's free. I put it up on the assignment page. All you have to do is download it and just open it up and make sure you say enable macros when you do. Okay. I put up a user guide, and I even made a short video last night to show you everything that you need to be able to do for Megastat to do the assignment. Okay, and so you can do it there. Also, if you go to the home page, take a second. You'll notice that there's now a data analysis page, and if you go into that page, it has again the link to Megastat, the link to the video, the Megastat handbook, and it has all the data sets from the book, because you'll need to start downloading the data sets to do this assignment as well. But you're welcome to use that or any other software you want, okay, to do your homework. So the next thing we're going to talk about is dealing with outliers. So an outlier is any data point that doesn't seem to fit with the rest of the data. So like with this example 10, notice how there's a couple points that are down here at the bottom that don't quite seem to fit in with the rest of the data. That could be a good example of an outlier. Now outliers can either be misrecorded data observations or they can be points that are really supposed to be in there. Okay. So if you have an outlier that's a misrecorded data point and you know, and you can go back and look at it for sure and realize that someone entered that wrong, you could try and fix it or delete it from your data set. Okay. But only if you're absolutely sure that it was misrecorded. If it's an actual true value, it's going to be giving you information about the population, and if you take it out, you lose that information about the population. So if it's actually some true phenomenon of the population, you want to make sure you keep that outlier in. So when in doubt, we usually probably are going to keep our outliers. But this is a good example of a true misrecorded outlier. Okay. So last semester, this really did happen. I asked students, what is your height in inches? So for example, 5 foot 9 inches is supposed to be 96 inches. Okay. This is the data I received. 5'5", 62, 62, 64, up to 76. What do you think happened here? Do you think I had someone in my class that was 5 inches tall? Okay, no. What do you think they did?
5 feet.
It was supposed to be 5 feet. Okay. And they just didn't read the directions closely. Okay. And so what happens is when I look at this data set, okay, here's my histogram. I have all of these nice heights that are from 62 to 76, and they look good, but then I have these few people in my class that are 5 inches tall. Okay? And because I know that that was a misrecorded data point, I can take those outliers out. I can remove the outliers. Okay? Or I could potentially change to 60 inches. Okay. So I would have the choice of just remove them or change them to 60 inches. But this is a good example of when I know that it was a misrecorded data point. Okay. And so something that I felt safe removing from the data set. Okay. And if I remove it from the data set, now this is what my histogram looks like. Okay. Notice it looks a lot better. I don't have that huge gap. And I can actually see a little bit more of the distribution now because it broke it out into smaller classes, and so I can see a little bit more of the shape. But again, when in doubt, if it's possible that outlier could be a naturally occurring observance, you want to keep it in so you don't lose information. The next thing we talk about is shape. Okay. Of our distributions, one way we can describe the shape is with the symmetry. And a distribution can either be left skewed, right skewed, or symmetric. So here are some examples. The top row is our symmetric distributions. Notice they are, well, symmetric. Okay, a left skewed distribution, notice that you have really long left tails, and the bulk of your distribution is actually in the right. So when it says left skewed, sometimes it's confusing to people to remember which one's left or right. I always think of left skew as a long right tail. Yeah, left tail, that's what I meant to say. Thank you. Okay, so you have a really long left tail, but the bulk of your observations are in the right. Okay, so since it's a left skewed, I try and remember that it is the long left tail. Whereas a right skewed distribution has a long right tail. Notice that you can either describe discrete distributions or you can describe continuous distributions. Either way, they can still be considered left skew or right skew. Now, in practice, it'd be pretty rare to look at a data set and find an exact symmetric distribution. Lots of times we'll say this is approximately symmetric or very left skewed or very right skewed. So in a left skewed distribution, the bulk of the distribution is in the higher values on the right side, but there are extreme low values on the left. Since the bulk of the distribution is the higher values, you might expect to see a high mean. So like for this example, if you ignored the tail for a minute, wouldn't you think that the mean would probably be somewhere like here if you ignored the tail? Okay, but because you've added these really low values, your mean is going to get pulled down. It's going to be lower than you might have expected. Okay, and so then your median, so if you start with a symmetric distribution, your median and mean will be in the same place because your median is your half point. But what happens is when you put in these low observations, your mean gets pulled down, and so your mean is actually going to be lower than your median because your mean got pulled down by those really low values. Okay. Now your median might get pulled down a little bit too, but not as much. So let's think for a while. Can you think of an example of something that would have a left skew distribution? So something in real life where you'd have a bunch of high values and a few really low values. Sure, there's lots of different things we can come up with, so just think for a second. Can you think of something that would have this?
Could you do like when people die?
Oh, that's a good one. I didn't think of that. So when people die, because the bulk of it should be around the 70s to 90s, but then you have a few infants, a few children. Yeah, that'd be a good one. Other ideas for distributions?
If you do the height thing, but if you had like some infants in the room or something.
Okay.
With children or something.
Okay, so if you did the height thing, but there were a couple children in the room. Okay. So let's see. Height of adults and a few children. Okay, so those are some good examples where most people are high values and you have a few low values. Now, right skew distribution is the opposite. So in a right skew distribution, you have mostly low values and then just a couple high values. Okay, and so once you account for those really high values, then your mean is going to be higher than you would have expected starting out. And so your mean is going to be higher than your median because your mean got pulled up by those really high values. Okay, and what kind of examples can you think of that might be a right distribution?
A tough test.
Okay, a really tough test. So if you wanted a left skew distribution, that would be a really easy test. So for a right skew distribution, a really tough test, okay? What if we change around the height of adults and a few children? Where can you think of that you would go that would have a bunch of children and only a few adults? Height of everyone at preschool. Okay. Now think money-wise. Can you think of something like money-wise that would be a right skew?
Salaries.
Okay. Usually something like salaries. And if you have just a few rich people, okay, so if you have mostly normal people and you throw in a couple rich people, what happens? Your average salary suddenly jumps up really high. And in fact, your average salary might even jump up higher than most people's salary put together. Okay? And so that's a good example of a right skew distribution. So symmetry is one way to describe a distribution. The other way that we really like is modes. Okay. Or maybe not that we really like, but our two most common things are symmetry and modes. So modes is just the number of major peaks that a distribution has. Okay. Now when we look at this, this is very subjective, and it's very much, if you just drew a rough curve over it with your pen, just very rough, how many major peaks would I have? So unimodal means one mode. Okay. And when you look at each of these examples, notice that there is mostly one mode. Okay, so here if I drew a very rough curve, it has one mode. On this histogram, again, remember I said it is pretty subjective, but if I was going to draw it very roughly, it looks something like this, and I'd probably still say one mode. Again, because it's subjective, you could maybe come back and argue with me that it has more than one major peak, but I'm going to go with one mode there. Bimodal, of course, means two modes. And so when I look at it, if I was to draw a rough curve, I kind of have a peak there and then a peak there. Or for this one, I kind of have a peak and another peak. Okay, or this one has the two peaks there. So it's just your number of major peaks. We're not looking at each bar, just the general overall shape. And multimodal technically means 2+, which means all bimodal graphs are still multimodal. This one could have maybe 1, 2, 3 modes. And over here we could have 1, 2, 3, maybe even 4. So like 3 or 4 maybe. A good example of a bimodal distribution that occurs in real life I've seen before is if you take the heights of everyone in a room with both genders, because what usually happens is the females usually have a normal distribution that looks like this, and the males have a normal distribution, but their mean height is just a little bit higher. Okay, and so you have these two curves, and if you measure everyone, then they're kind of overlaid, and what happens is when you put them together, then you get this bimodal graph. So lots of times, if you look at data sets and find two modes, that could mean that you have two distributions that were put in together. So, questions at this point? So our next section is 6.3, sample statistics. I think this is a good point, though. Let's take our 2-minute break.